Welcome to episode number 55 of the Piezo SHOCK Show. Today, I'm going to answer the question, does an ultrasonic dental transducer degrade in performance with increasing power? So I'm going to describe, obviously, what does degrade mean and what is the amplification mechanism by which we're going to be driving the power to our transducer higher and higher. So first, I'm going to show my setup here. So I have a function generator, which goes into this op-amp amplifier right there. And we have the power supply, bipolar power supply. So this is a dual power supply. So we have 30 volts, but this is located in series. So I'll put a link to what this is. I think it's called, I forget, bipolar power supply or dual voltage power supply, where we actually have a ground. So this is positive 30 volts, this is negative 30 volts, and this is ground. So it's actually put in parallel. So you have a ground connection. So it provides the power to the op amp, which then goes through this transformer, gets bumped up. And then it comes around here and it goes through a 10 ohm resistor on the ground side. And here we have our transducer right down there. So that's our whole setup that we're going to use for driving the transducer at higher power. So no, we're no longer using the drive circuit that we were before from the device. We're actually using just the transducer itself. So here's another view of it. Here's the function generator. Here's the op amp. Here's the power supply for the op amp, plus and minus 30 volts because I pressed this first button here, and you can see this number. This is a TP3005D. It's some Chinese brand, and we have this transformer. We have an input, and this is a kind of a handy circuit that you can just purchase directly off eBay, off Amazon, wherever you get Chinese electronic components. You will find this product. I'm not using this big transformer. This is an audio transformer. I end up using something that was advertised as a ultrasonic transformer. I just wanted to make sure it had high frequency response, but anything that's rated for a boost power converter, basically you could look for PCB transformer. Usually those will be good, but you just do need to make sure that when you're testing them that they work at higher frequencies. That's the only difference there. So I will actually begin testing. And there's a setup again. I'm going to begin testing, and I'll share my program here. So I'm going to go from 30 to 40 kilohertz right here. And I'm going to go in increments of 100. We have a 10 ohm resistor. This is delay time. I'm going to set the probes to 10x because I'm measuring higher voltages. This is different than the other programs that the other times I've used this program. Now I'm actually going to be using this through through some voltage probes. So the voltage probes, actually, if I did show you here, the voltage probes are actually inside this box down here. So there's a picoscope, oscilloscope, and I can kind of show a little bit of it. Let's go there. Let's go for a field trip, shall we? So that's the oscilloscope. It's connected, and there's like actually inside of here, this is hot. That's pretty hot actually. There's some voltage probes, as you see, and there's a 10 ohm resistor on the ground side there. So we are measuring everything through there. There's our transducer. I'll just look through the microphone here. Oh, there we go. Okay, that's your transducer. Well and good. Okay, let's go back to our program. So we're going to be using higher voltages. So I just want to start. You can't use 2 volt voltage because of all the amplification. Let's use, so the way you do this in my program is we have a feedback control, and let's just use 5 volts. And let's see if I can get that with 10% tolerance, because the low voltage small steps in the amplifier are going to small steps in the voltage. So there's basically going to be a closed loop control of the signal generator. So let me just show that again. There'll be closed loop control of the signal generator in order to achieve constant voltage. across this regime. So 5 volts is kind of small. Let's see how all of this works out. So let's just start the sweep. We're starting at 5 volts, right? Everything is, I think I connected everything before properly. So this is about 5 volts right there. And the command voltage is 50 millivolts peak to peak on the screen there. And let me see if I can't get that for you. You see that? It's like it's in a sweeping frequency, and it's keeping voltage what it needs to be in order to consistently achieve those parameters. So let's go back at the sweep finished. So that's 5 volts. This is like time. This is what happened to volt. So this is no, there's a couple of different plots here. So this plot is voltage versus frequency. Blue is voltage and F is frequency. So you see how the voltage is changing, and it's keeping within the tolerance, but it's obviously going up and down. And I just want to actually change this commanded voltage on channel on this other channel. So the commanded voltage is in red. So the commanded voltage really didn't need to change very much across this realm. But 50 milli, because the impedance wasn't very high. So I think it ran okay there. But let's go to this plot. This is what we really want. This is impedance, and this is phase in red. So we see that resonant frequency at 36.6 kilohertz. Usually, I think before we were finding that the auto sweep was going to 36.9 or so. So that's approximately correct there. So we are going to analyze this a little bit deeper. Let's start by doing something here. So I'm going to do a couple of things, and we're going to have fun, right? That's how we do it. We're going to write the impedance, the resonant frequency, and the voltage. So this is 10 volts, and this is all in RMS. I think it's an RMS. Ooh, I want to say it's actually it's not an RMS. This program works in amplitude. Okay, let's just go by voltage. So, and I will spare us from doing that whole sweep. I'll start from 34 kilohertz, and I'll end. And we're not gonna worry about anti-resonance. So I'll end at 38 kilohertz, and I'll go in steps of 20, and that should be good. So now I'm gonna rerun this. We still have the same 5 volts. So we're just running a frequency sweep. There is a closed loop control active, but it's we're kind of maintaining that 5 volts is not a problem here, even though the command voltage is varying plus or minus the tolerance. The step size for the voltage is going to limit us. So I don't know how close we're going to keep. So let's see here. So this is pretty good. There's a little hiccup there. Okay. So we already got there pretty much. So resonant frequency 36.6, 3660, and I'm just doing this analysis like how I might actually do it in practice. And this is 1.09 kilo ohms, so 1.09. That's the impedance in ohm, and this is the resonant frequency in hertz. Okay. So let's just skip around. Let's just do 20 and then 40 and then 100. So let's do 20 volts. And we can reduce the tolerance now. Let's see what voltage we got to now. So now it's using about 200 millivolts. Seems to be hitting one of the right at one of the stages of the oscilloscope. Hence, a lot of clicking I can hear right now. But no matter, our resonant frequency is kind of unscathed there. Yeah, we're just kind of right at that tolerance where we have a lot of clicking going on the oscilloscope. Maybe like 21 volts would have just probably rang fine. But anyways, our main frequency is okay. So 36.5. We did 20, right? Okay, we did 20, I believe. So 20 volts. So 36.5 and 1.176. So we did have an increase. Now I will try. We're going to go in increments of we're going to go in dual increments. So we'll do 40, 80. I don't think we can get to 160, but I think we'll get 120 just fine. Okay. And I want to do something here. I want to for this one, I'm going to put power. So we'll log the power, the maximum power we get to, which is here in this case about 375 milliwatts. So I'll write power. And that's units of milliwatts. All right. So we'll just continue going forward and taking the data like we might. Okay. Shall we run again? No, we're at 40 volts. So we're actually starting to see some nonlinearity in the voltage, but I'm going to ignore that for now. 36.4. Nonlinearity because the curve going into the resonance right here is sharper than the one coming out. There, because as you increase in frequency with a large voltage, as you get closer to the resonance, the amplitude goes higher. Because the amplitude is higher, the resonant frequency decreases. That's the tendency as amplitude goes higher. So it kind of becomes nonlinear as the material properties change. Now, a way to address this would be we do a constant power frequency sweep mode, but that would take a lot of variable voltage. So at off resonance, you would have a lot higher voltage needed than in resonance. But we're just going to continue this conversation as is. 1.12, 1.120. Not much change there. Let's take a look at the power in red. So we got to 1.4 watts. So let's just do 1400. Let's keep it in milliwatts. Now we'll do a sweep at 80 volts. Okay. 80 volts. And I think on my screen we're at, okay, so let's do 80 volts. So it's getting to the resonant point there. All right. I mean, it's getting to the right voltage. Yeah, that was a pretty sharp drop right there. I'm going to still ignore it for now because we're just learning here. 36240. Now, what you normally would expect is this number to keep increasing, but because of the drop occurring, it won't happen. You will get, depending on where it drops to that nonlinear area. And I have a couple videos. If you search resonance nonlinear Piezo SHOCK Show, you'll come up with a couple of videos. One of them I have, like I'm showing a notepad with this exact phenomenon. Go to that video and watch it closely, and you'll kind of get a better idea. But here we go, 36240 and 1.1040, and let's just check the watt level. Let's say 5.5 watts. That's getting pretty high. Now let's just try 120 and we will call it a night. Actually, we won't call it a night. We'll call it a day wherever you are in the world. We should be able to get there just fine. Here we go. It's 80, it's 90, and we are in business. taking a sizable amount of current there. Yeah, see that big cut? That's not because the program is not adjusting properly. It's actually because it's actually because I'm just going to turn the output off right now. It's actually because we are nonlinear, severely nonlinear. 36120. And the impedance is 1119. Normally we'd like to see the impedance go higher and higher, but that's not happening today. Not today. It's not happening simply because in the watt is almost 10.5 watts. So we're just going to plot this here: voltage versus frequency. All right, we see this voltage start to drop. You'd probably be able to put a linear plot to it. Let's try impedance. That's random. Let's try power. That's exponentially increasing. Obviously, power is there's IR squared, right? I squared R. So I is the current is approximately proportional to the velocity, and the velocity is sort of linear increasing with voltage. So that means we actually have an exponential increase in power as we increase in voltage there. Are my screenshots on? Yes, they are. All right, so we'll be able to provide that. But this is not a good test because of this nonlinear that exists here. It doesn't work well. So I'm just going to go ahead and lower this amplitude so I don't have to worry about that. Okay. So what I'd like to do here, so I've actually already done some of this before, and I can tell you that doing constant power frequency sweeps here, I'm going to do it for you actually. We had 10 watts. I'm not going to give you 10 watts because that's not going to be practical for me to do. I'm going to give you 3 watts, and I'll just show you how it can be symmetrical. I think if I start from let me just do this. Let me start from 35.5. So I'm kind of picking out numbers here. And I'll do 4 watts. So 35.5. Basically, I'm trying to zoom in on the frequency because if I get too far, and I'll stop at 36. I'll stop there. And I'm going to do a constant power frequency sweep now. This will be quite telling for you guys. So PID, power, and I'll just do it. Actually, I'll do 1 watt, Let's do 1 watt. And I'll do I probably won't be able to get away with doing the whole sweep because at this point, if I'm driving the transducer here, I'm going to need a lot of voltage in order to get it to behave appropriately. So I'm just going to start it and see how this goes. Constant power frequency sweep. I'm not going to be able to get much higher than that. Yeah, okay. Okay, see the power is required. All right, that's the resonance here. Okay, so I'll talk about what's going on right now. So what just happened? This is the actual voltage and power versus frequency. So as you see here, voltage, it needs to be very high in order to achieve that 1 watt power. But as we got close to the resonance, the voltage needed to be low. And if you see this power, although it looks like a lot of random noise, it's actually just hovers very closely to 1 watt. Now, I probably would like to have started this from 35.8 so I don't go excessive on the voltage, and change that to 6. And I think we'll be good. So it's going to scoot the plot forward from there. So let's try that again. So it won't nearly need as much voltage. That's the idea there. Hopefully I don't stand corrected. Nope, that's good. Got to 154, which is higher than I would have expected, but that's okay. And that's a good, nice symmetrical resonance happening there. And this device is with the tool on, I think the tool adds a lot of impedance, and so does the holding mechanism. Therefore, we're not really able to excite this with a lot of power and get the my expected trend, which would be as I've seen in many other transducers. As you increase power, you'll reduce in voltage. Sorry, in impedance. So this didn't really happen. It's kind of random, and depending on also how you measure, you'll get different impedances. And obviously, and with this constant power, since it smoothly goes across resonance, you're not getting that drop, and that drop actually gives you a false high impedance. If we looked here, 3 watts would be somewhere around these two. We actually got if you drove it with 3 watts, so 3,000. We actually got an impedance of about 880, which doesn't exactly fit that. And we got a resonant frequency of 36240, 36240, which is similar to the one received here, but we are at what voltage? So it also tells the voltage. If you go here, we'll know that at resonance we're only at 30 volts. So it does give you different results, which can, you want to be consistent in the way you are testing, and this is the consistent way to use constant voltage. So let me now. What I'm going to do now is I'm going to pause the share, and then I'm going to actually let me just take off the tool while we're here. Let me get my little wrench out. Actually, probably unpower the device there. And I'm just going to remove this tool, and also I'm going to remove the transducer from the holder because I don't want it to be. It's probably a little bit hot. Also, I'll remove the transducer because I just want to test the transducer itself right now. And I want to actually show you that trend, which happens. I'm removing it from this holder. I probably won't touch it then. It's getting to hundreds of volts. Okay, and I'm just going to put it on top of something here, not something plastic. But paper is fine. Usually you have a sponge laying around if you're an ultrasonic dude, but if you don't, God is gracious. So let me show you what I just did there. There, I just put the transducer, took it out of the case here. Also unplugged one of my lights. Plug that back in. Okay, and we're back in business. A little bit hairy with all the cables right now, but life is good. It's actually what you make of it. All right. Yeah, so we just have our transducer. So I want to redo characterization. The way I would redo a characterization is just do like a 30,000 hertz to a 50 actually. And I would do increments of 100. And this is a similar process that you might do for investigating your transducer in whatever system you're using. I would do voltage, and for this type of device, I would just go 10 volts, which shouldn't be too much. So let me just run that sweep. All right. Hopefully we won't have too much trouble because I put the tolerance as 5%, but it seems to be going just fine. So I'll read so this is a transducer by itself. So it's going to have a resonance like around 40 something, 42 kilohertz, 40 kilohertz. And just to show you that transducer again while we're waiting. There she is. Beautiful. Our transducer of the hour on a piece of paper. Don't touch. You might get shocked. Okay. All right. There you go. At 44. Higher frequencies are naturally going to be higher power and lower impedance. But in this case as well, we don't have a tool on the device. So we also do expect that. Our phase gets from -90 to 70. And let's start to do a higher power sweep from 42 to 46. 42 to 46. And let's just do a little bit more fine, just so we can see what we're dealing with. We are just, this just takes a little bit because it's doing its amplitude adjustment. There's also a delay time I put in here in case there needs to be anything to settle out. It looks fairly symmetrical, the resonance point, although although we are using constant voltage, so it's not really stressing it too much. And if you look at the power graph, we're now at 150 milliwatts for 10 volts. Okay. So, okay, well and good. I'm not going to repeat the constant voltage. Sorry, I'm not going to repeat the constant voltage test because that's actually not correct. I mean, it's not the most correct to do. So this was done with, with the tool, and we're actually going to do it without tool. Just bare transducer. These are still my happy points that I like to take. I'm going to log this here as 10 volts. I'm just for the sake of putting it down. So 43,880, 43,880. Then the impedance is 647. We're going to be able to put a decent amount more power into this. And the power I got to at resonance was about 150 watts. So, but now we're actually going to start with power. So 150 milliwatts. So let's just do actually 150 milliwatts. It's for lack of a better number, because as you increase your frequency, you're going to have to be stepping back slowly. So let's start from 43.5 to 44.5, and frequency up to 20. The PID, it's not really PID, but it's just feedback, is around power and 0.150. And the tolerance is kind of strict, but let's keep it. Let's keep it at 5%. So let's just run that sweep. So it's going to do controller on power. And you notice in this case, I didn't use the picoscope function generator to power to input into the amplifier. This amplifier is great because it actually has a preamp built into it. But I think it's struggling here to get that right number, but that's okay. Actually, it's not okay. Set it to 10% and it'll be fine. Because the grounds are going to get screwed up because the oscilloscope probes are connected after the transformer, and the input, the wave, the signal generators before the alp amp, and all the grounds get screwed up, and you end up getting short circuits and stuff, and too much current passing through just because you have your grounds messed up before and after the transformer and the amplifier. So the external signal generator allows me to bypass that ground, because that oscilloscope is actually indeed floating, because my laptop is floating. Even it's connected to the power outlet, there's no ground. So here we are. Okay, so let's just do that. So we have 646 ohms. So this power is 150, so 646. So true to its word. And 4380 And voltage, let's check that. That's gonna be interesting to see. Voltage is about exactly 10 ohms. So it just matched in this case. So it's probably linear close to this range. So let's do 500 milliwatts next. And I think I will like reduce that just in case there. And let's do 500 milliwatts. And then next, always we're going to do 1 watt and kind of keep going forward. Okay, perfect. And the resonant frequency is obviously not at the bottom because it's going actually after admittance. So 43860. That's it. Am I able to copy that? Yeah, I am. So the resonant frequency decreased 20 hertz. And the impedance is a 667. I think what we're going to end up finding for this device is you're not actually and the ohms value is about 18 ohms. I mean 18 volts. For this device, it doesn't seem that you can actually put a whole lot of power into it, just because where the transducers are, probably it's not exactly at the nodal point, and you are kind of way under what you won't be able to drive it even with 100 volts. Maybe you have a few hundred, but we're going to try our best to really stress this. And if we break it, then we're going to be on camera. We're going to have it for us. So it's still, as you're going to see, it's still alive and well, but not if I can help it. All right, let's try 1 watt. And 1 watt's still not a whole lot. And I'm going to make that 5% because we're in a higher voltage range now, so we can afford to be a little bit better on the accuracy side. Okay, and now we're off. Okay, so 43800. Okay, that's where. Okay, so that dropped 60 ohms, so that tells me we're at 699. So it's still not very high increase. It's only increasing a little bit. 1000 milliwatts and let's say 18 volts. I mean, let's see. Well, what kind of power? Well, we know the power. The voltage is about 27 volts or so. So, still pretty doing okay. You want to try 5 watts? Ooh, let's try 2. Let's go up in terms of 2s. That's always seems to be best, because then we'll run out of space to go, and then I won't have a long enough video. Is that ever a concern for you guys? Let's call, oh, I'm going to say it's 750 ohms, and I'm just going to mark another number down there. It's going to be 43400 and 50 volts. I'm just going to throw numbers out there because I can. All right, we got to 40 volts, so not quite 50, so we got to 40. The resonant frequency ended up being 43.7. Oh, now it's a lot lower. Actually, 43.700. And the impedance is now 695. Did not change much at all. Probably with an experimental error, because 2 watts is definitely higher than 1. And the resonant frequency decreased only by 100. Actually, by 100, which is more than what it was before. Before it was 40. Let's keep going. Let's try 4. I'm not interested in redoing measurements because that's not what I'm here to do. So I'm doing 4 ohms. I mean 4 watts. We only 43, 4, 5, 5. We got this number one. This actually got pretty low now. I think I'm going to stop that. And I also probably want to disconnect the power right now. Okay, because it kind of got hot. Okay, let's just leave it at that. So 43,540. You got that one. Impedance out finally started increasing 708, and the power was 4,000, and the voltage we got a okay. No, we didn't get a spike in voltage. We got about 55 volts. All right. Do you think we can do 8? So now when you're kind of getting this range, you got to be a little bit careful with how you do your how you do your frequency ranges. If you want to get the maximum power because of the voltages. So let's do 8 watts. Hopefully I get to see it happen. Hopefully 8 watts is something that we can establish. Okay, so it is going. So once it hits its minimum, I'm just gonna stop it so I don't have to run this excessively. Yeah, I can just stop it there. There's no need to have it continue. Okay. All right, so 8 watts, 43,360. And then finally impedance is increasing? No, 695. It does not want to increase far than that. Now this is like, this is the trend I didn't want to see. I didn't want to see the impedance consistent, not changing. That's not supposed to happen. It's apparently not really loading it too bad. And it didn't just 75. So it did increase, but it didn't like it's kind of stabilized, which is not it's not typical for me to see that, I'll say. But what I will want to do right now is let's see if we can get it higher. So let's start from 43.2 or 43.1. And let's just go for a higher power. Let's go for 10 watts. I don't think we're gonna get too much higher than that. We're going to, if we just plot this plot against this one, I guess the frequency is going to be the most telling there. So this is frequency versus voltage. That's one way we can do it. We can also do frequency versus power, and now power is on the y-axis, but bear with me now. Now impedance didn't seem to really play well. I'm not one to judge, but yeah, this is probably going to be a little bit nonlinear with power. Voltage maybe make more sense. Actually, current's going to be our friend here. Let's assume that so current would probably have been a better focus, but you know, I got what I got. So usually we would do current. So current and frequency, which current is proportional to displacement. So that's that is a linear change, but that change in frequency itself is a nonlinear phenomenon. Now I do feel like I have a buzzer laying around. I'm gonna pause this share. Okay, so we see here we have this buzzer, and I'm going to hit that with some power, and I'm just want to go a little bit close to show you what it looks like. Because if it does break, then we have a nice before and after of that. So let's continue here. Let's get this a little stable. Okay. So With that, let's now test the buzzer. I want to kind of put down the amplitude there of my function generator. Allow it to kind of soak up that. And I don't know if this probably amplifier doesn't like probably low voltages, but I mean low frequencies. I'll set it to 10 and 10%. And let's just do 1 kilohertz to 50. And let's see what that sweep looks like. The frequency and resonance. That's a resonant point right there. So this is again running that buzzer. You might be able to hear it. I'm not sure. It's squeaking pretty loudly here. Obviously, I'm right next to it. Let's check the power. The power got to 100 milliwatts. And the impedance, as you can just use it before, impedance got to below 1 kilo ohm. So we'd probably be able to hit it up a bit, but at lower frequencies, we may not have that voltage gain. But we ought to go by more than 100. This should be 100 at least. Let's just try 100. There we go. Probably good that I have these earbuds in there just in case the high frequency. I don't exactly know what the effect is going to be. You can tell it doesn't like it. It doesn't like high voltages at this high frequencies, but it's gonna. I wanted to see its radio mode come out, but we can just try as well breaking it at the lower resonance. That's probably going to be a better option for us. Where does it lie? Where does that radio mode lie? I haven't measured this one in a while. Maybe I should have done a higher mode, higher. There is another mode here. I'm telling you. I wonder if it was that third 27 kilohertz mode. Didn't like the higher voltages. We are just getting there. The voltage seems a little bit low. It seems to be hitting some stages on the oscilloscope, but what kind of power are we at? The power in the red, which is real power, it is high. So probably, relatively. So we did not hit another resonance within this realm. I wonder if we could go from 50 kilohertz to 100. And let's do increments of 250 instead, just to get it to behave a little better for us. Actually, yeah, this voltage is too low. Well, let's just focus on that lower mode. Let's just do, what was that, 1,000 to 10,000. We're just going to focus here right now. And let's just see what happens when, so we'll go 3 to 5K. 3 to 5K. And I'll go by hundreds, and we'll do our loop. Let's start with 10 volts and see how that gives us. let's do 20 volts. So what power did that give us? That gave us 10. Oh no, that gave us 80 milliamps. Let's do by 20, and let's do 100 for let's say 50 volts. Now there's suddenly another another resonant mode which comes. Now it's still ringing pretty loudly because at 50 volts, I think I touched the edge. That's not gonna do anything, but what am I trying to show you? I'm just trying to show you, well, oh yeah, let's do that. Let's do the thing I was supposed to show you. And it's gonna be ringing in my ear. Okay, so we're what power are we at? We're at in the purple. We're at 3.2 watts. I'm just gonna do a PID on power, and let's do 0.1 milliwatts. So that this transducer didn't really work that well. I won't do current again because I'm trying to capture power changes in impedance. Actually, we can do current, but it would have to be real current because this is a device which doesn't. So 36 is the resonant frequency. The power is 100 milliwatts, and the impedance is. And actually, I'm going to switch to admittance. The reason I'm switching to admittance is because admittance and also real admittance is because we're now kind of working in with this device. It has low coupling, so the impedance is strongly influenced by the parallel capacitance for this device. So I'm going to be using admittance. So that's 936 micro, which is 0.1 milli. So all right, Y R in terms of Siemens or millisiemens actually, 0.956. And the voltage, I don't really mind that right now. I'm just gonna go for, this is the buzzer. Let's just keep going with this, and let's keep popping up that power. And I think we had fairly enough voltage to go around. So I'll just pop it up to 500, 0.5 actually. Keep that at 5% because we can, now that we're a little bit higher. So 3520. And the admittance is increasing to 1.02 milli, 1.02, and that's 500 milliwatts. So it's kind of following what is expected. How are we on voltage? 50 volts, so we still should be good to go in terms of that. Okay, let's try 1 watt. Still looks okay, didn't break. All right, let's just see what we got here, 3400. And admittance is 1.04. And the power is now 1 watt. It's still holding up fairly well, although the resonant frequency is decreasing. How are we on voltage? We still weren't too bad on voltage. So we're going to continue to increase the power. 2 watts. Is loud. Okay, 3260. And the impedance is decreasing. Now, I mean, this is not typical. That's all what I can say. I haven't tested a buzzer in this fashion before. I can definitely say this is not normal for probably what's happening is the coupling factor is getting really nailed, and what we'll see here, if we plot impedance and phase, we do have, I mean, we still have a similar low impedance, but the coupling factor, there's another kind of resonant mode, I think, kind of occurring there. And how are we on voltage? Can I pump it up more? Yeah, it's not too bad on voltage. So I think we can continue to output. Now I'm going to definitely guarantee you're going to see less amplitude, because it doesn't seem any louder. Doesn't seem any louder than it was before at the lower power. So now we're increasing power. You're probably not getting as many decibels, although this impedance right now is not changing, which is not something I'm used to seeing. But I believe measurements, and almost they're incorrect. So this is actually pretty cool. Let's and how much power are we able to get? 2 watts into it. Let's just try 5 watts. Let's see if that'll even work. I might have to shut something down if it gets too hot. Something started burning. So I don't know what. We did get a crack. Okay, we did get a crack. Actually, what started burning? Let's stop this. Did our transducer start burning? Our amp is pretty hot. Let me just kill that. Let me reduce it back again. Ooh, I think I blew out the amp. Yeah. Anyways, that was great, because that was the last experiment I'm probably going to do with this amplifier, because it seems to be broken. Anyways, so we had I can show you here. All right. This transducer broke right there at the edge. You can kind of see, let me back up there. Yeah, it kind of broke, see that hairline fracture right there from one side to the other. So it did break around the electrode. So we did have some fracture, although not in the exact way the catastrophic failure I would have expected, but it makes it for a good video. You've been watching episode number 55. I basically demonstrated, does an ultrasonic dental transducer degrade with increasing power? I think what we're going to find here is that the power, no, it wasn't measuring actual vibration amplitude. I think you're going to find that as you keep increasing power, you're not getting more, you're getting less and less output per increase in your power. In terms of output increase, in terms of displacement, now there could be other reasons why the impedance itself doesn't decrease with power, but I think, well, the data tells it all. So thanks for watching this video. I look forward to kind of having you along on the next one. Probably, what I might talk about in the next video is we might try to do some hacking of that driver circuit and maybe build up our own MOSFET circuit with the push-pull and try to drive it ourselves using that transformer that was inside of the driver circuit. So I'll see you next time. Feel free to check out the links. Also, I do consulting for ultrasonic transducer development. You can check out the links for understanding more about those services and if they're right for you. If you're developing a commercial product, most likely I can help you out with many of the challenges that companies commonly undergo while developing such transducers and driving systems. All right, catch you next time.